Perfect. Okay. Welcome. Yeah, exactly. Welcome to improving NetDump hardware support and performance with IFLIB. I'm Sam Gwydir. So who am I? I'm a last job Groupon. I had a need for coredumps, but without a swap partition. So I had a whole year where I did this odyssey about learning about different ways you can get a coredump without large swap partitions. And there were sort of two answers there. Dump to a zvol, if you're using ZFS, or netdump. But neither of these existed in FreeBSD. Later it turned out actually there were netdump patches, but I didn't know about them. But I left that job, so I didn't use either of those things. So I didn't work on them. Now I work at Joyent. My team is working on FreeBSD as a hypervisor. We have machines with over 1 terabyte of memory. And we can, again, not dump because we don't have large enough swap partitions. We actually have swap partitions this time. The machines are actually partitioned correctly. But partitioning 1 terabyte of swap is crazy. So, why am I motivated to do this? Coredumps are an important debugging tool. We don't want to leave our hypervisors just panicked sitting in DDB. I just want the core, and then I want to reboot the machine and get it going again. Swap partitions are large enough to fit cores from large memory systems that are impractical. A lot of our machines are using flash, so it's also expensive and possibly not even possible. We have a lot of machines networked together. Hopefully only a few of them are panicking at one time, so we can dump to the other ones. So netdump is practical, and also an existing solution, but it can be slow. So if you're dumping 1 terabyte over like a slow system, this might take an hour, and that's far too long. And also I was motivated to learn about IFLIB and writing drivers, so it's a good project. So it turned out, when I started looking into this, that netdump had been around for a while. A guy named Daryl Anderson started working on this at Duke. It was in the there it says, yeah, FreeBSD 4 days. He had patches ready to go that worked. And this is the same work that we're using now, but it's just been updated over time at Sandvine and then later Isilon. In 2017, while I was at Groupon, I tried to use these patches, but it turns out they needed to be ported up to FreeBSD 11. They're very old still. I think they only worked for 9 at the time. We were running 10.1 at Groupon. But Mark Johnson, who had an updated patch set at Isilon, released a set of patches for me and whoever else, I guess, was asking. And he's maintained the currently working version on current GitHub. So this is actually a diagram I made for my last talk. But so you can see over time, the way people have coredump has changed. It used to be just to a line printer, which would be very slow. Later to magnetic tape, then to swap. You can still do that. And then hopefully now we can do network dump. The standard dump process is pretty simple. So you dump all your RAM into a swap partition, and then you reboot. And then upon reboot, you run a program called SafeCore that reads off the swap partition and creates files on your file system so you can later use them in bar crash. The swap partition looks like this. When you dump to it, it dumps to the end to allow for a few programs during boot. I think FSCK is the main one that wants to use swap for whatever it needs to do cleanup. So hopefully FSCK doesn't start overwriting your dump. So that's right to the end. The netdump process is a little bit different. So when your machine crashes, you take all the memory, dump it out in stages to a couple of reserve pages, 8 of them. And then a UDP client starts after you crash and starts shooting UDP packets at a pre-configured dump server. And then that server writes it straight to the file system. So there's no need for a large spot partition or anything like that, so it's a lot more convenient. You get 3 files, the same as a normal core dump. You get your info file, the core.txt, and the core itself. So as of April 2017, the patches I started working on, Netdump supported 4 drivers, and it had to be written specifically for each driver. And the code is mostly the same, but it had to be tailored to each driver's functions. And so that was a Broadcom driver, PGE, okay. A couple Intel drivers, EM and IGB, and then VMX, which is the VMware driver. And then netdumpd was pretty simple. It was uncaptionized. Now, a bunch more drivers are supported. This is mostly Mark J's work. A few more drivers are done. In particular, vtnet makes things really nice. If you're developing in Beehive, I actually had to buy a separate machine because when I was originally working on it, I couldn't use a virtualized environment to just dump to a Beehive VM. So that makes things really nice. And then, since it's been ported to IFLIB, simultaneously by me and Mark Johnson, I emailed him when I was finished, and he said, "Oh, I did that too." I was like, "Oh man." But so now it supports EM, IGB, and IX. And in addition, it supports compression support, so both gzip and zstandard coredumps are supported. And netdumpd is capsicumized, so it's sandboxed. Okay. That's where we stand now. So let's talk about how you design netdump. It has to be, it's not just, you can't plug in directly into the normal TCP/IP stack, because once you've panicked, you can't really trust the system that panicked to do your dump correctly. So you have to have your own set of tools that you can reach for in panic context. In addition, there's no interrupts, no dynamic memory allocation, no access to the TCP/IP stack, and on top of this, it needs to be simple because you don't want your netdump stack to panic. Again, it can't break, so it has to be simple. So there's 2 parts to the netdump process. There's the client, which is the machine that panicked, and then a server running netdumpd is a netdump server. You configure the netdump client with dump on, like you'd configure normal core dump to swap, but instead you tell it, not yet. You tell it the server, the gateway, and your IP address. TCP, so you have to give all the information. So upon panic, the netdump client dumps a little bit at a time to these reserved memory pages that you're not using, so you don't overwrite the memory that you're intending to dump. And then you start up a UDP stack that slowly shoots out these UDP packets toward your netdump server. And so there's 3 main steps. You give dump on an IP address. So once you crash, the UDP stack tries to figure out the MAC address of the IP you gave it. Once it has that, it starts transmitting the header. And then once that's done, the core itself, and then one final packet to say, hey, I'm done. There's a couple problems with this design. It's statically configured. So once you set this IP address and your server crashes, you can't actually change the IP you're dumping to. So if your network topology has changed, the IP address of your netdump server, you change it, and you forget to reconfigure all your hosts, they won't know which server to dump to, so you won't get your dumps. It'd be nice if you could resolve DNS, so you could just say, hey, netdump.joint.com is our netdump server, and resolve that once you panic. Next is a fixed window size. We'll talk about this later, but it's currently just a bit field at UN64. So there's just 64 packets you can keep track of at a time. And it does not deal with packet loss well. It slows down dramatically in the face of packet loss. So it is UDP, but it actually does have a system of packing the packets, but it's very, very slow. I'll talk about that more later. And it doesn't scale. The NetDump server doesn't have an ability to slow down the transmitters, so there's no congestion control. So if you have one server dumping to you, it's probably fine. If you have 10, you're going to start dropping packets, and all these servers are going to slow way down. They're probably all going to time out, but your dumps will take longer and longer and longer as you drop more and more packets. And it doesn't support all NICs. You have to implement support per driver, except for IFLIB. So expanding IFLIB driver support would be very nice. And then it's IPv4 only. There's some solutions. So we can teach NetDump to resolve DNS. I haven't planned to do this yet. That'd be pretty nice. And then it doesn't deal with packet loss scaling issues in the fixed window size. We can implement TCP-like congestion control on top of UDP, and that'll fix some of that. That's the main part of my project, besides the port to IFLIB. And if we expand IFLIB support, then we get NetDump for free, because NetDump only needs to be implemented once for NetDump, or for IFLIB, and then everything it supports gets NetDump for free. So that'd be nice to expand IFLIB support to vtnet and others, so we don't have to write it special. I don't have any plans to support IPv6, so just don't use it. So what does using these two commands look like? They're pretty simple. So dump on supports two kinds of compression. The big Z is Z standard, small Z is gzip. You can optionally set a gateway, but right now you just need to set your server and your IP that you want to advertise to the server, and then the interface. It's pretty simple. This is what I use on my vHive system. You do have to, which is inconvenient, but you do have to set dump on to off. Dump on off or dump on dev null will clear all the configuration before you actually run this. It's kind of inconvenient. And then next, this is how I run the NetDump server. This just says don't demonize it. Everything else is optional. The port to IFLIB. I started with Mark Johnson's patches, which didn't yet have IFLIB support. Every driver had separate support written out. My experience was actually pretty good. It was pretty easy to take the existing EM driver NetDump and translate it into IFLIB. But the IFLIB documentation is not complete. I know I worked with Matt Macy for some of this, so I could ask him directly. I know other people would have a harder time trying to figure this thing out. Originally, if you did like man-k or apropos IFLIB, it came up with nothing. You actually had to know that you were looking for IFLIB-DD, IFLIB-DI, and IFLIB-TXRX, which is the device-dependent, device-independent, and the transmit-receive functions separately. And then on top of that, there's KOPT functions that aren't documented anywhere. So you actually have to go through, and you won't find them in cscope because it doesn't read KOPT files. So that part was particularly difficult. There were some things that I needed that just didn't exist in the C implementation. So it's mostly fairly simple. IFLIB sort of resembles all the function names, and interfaces resemble EM, so it's fairly easy to translate. But the hardest part, the one thing I didn't know, there's sort of a magic go button, which is what Matt Macy called it. And it's not described that way, it doesn't seem that way to the user. And so I sat, I think, for a week or two, not sending packets, trying to figure this out. And what I was doing wrong, and it just turns out one function is missing. So it'd be nice to have like examples of programs that use IFLIB, or drivers that use IFLIB, and that you can base your work off of. So I guess everyone after me will benefit from me as an example. So there you go. So here's a comparison of what these two look like. This is actually vtnet on the left, netdump support because it doesn't use IFLIB, and then on the right is the IFLIB netdump. So you can see it's fairly analogous across each of these sort of like paragraphs are analogous. This is exactly the same. And so is this. So it wasn't too hard, and that was nice because that's the whole point of IFLIB, right? It's to be easy to use. Okay, so now we're going to talk about the UDP stack. There's two parts of this algorithm. One loop that does all the transmitting, and then once that loop is done, you pull the NIC for ACKS, and then once you're missing one, you go back to the retransmit stage, and then you loop this until you get all your packets through. The transmit stage, there's the retransmit label that you go to when you miss a packet. But so you start through, you try to find the packet length you're going to use. Generally, it ends up using the into minus the headers. But if it needs to be smaller, you can bound it by what's left. You know, so some odds and ends at the end of your buffer. You'll use a smaller buffer, a smaller packet. On the retransmit, if the packet has already been ACKed, you have to go through all of them and check, have I already ACKed this? But if it has been ACKed already, you add the length, packet length, and then you skip the rest of this loop. After that, you fill out your UDP header, get your mbuff, you place all your header inside, and then transmit that over the wire. And then you set in a bit field that this packet has been transmitted, and then you add that length, that packet length, and loop until you transmit all your packets. I'm going to draw this out after we talk about the ACK part, so you'll know how for this performs when you lose packets. Okay, so next, you pull for all your ACKs. So while the received ACKs bit field is not the same as the ACKs you want, you go through and you pull a maximum of 10 times. And if you pull and it's not ready, do a retry. And if you retry 10 times, then you time out. You don't do that. And then each time you go for a retry, you print a period and go to retransmit. And then if you don't retry, or after all that, you pull the NIC for a packet. It takes about a second or two each, and then you wait 500 milliseconds. And then if you do successfully receive this, you increment the sequence number, the number of packets sent total throughout this whole process, and then go, if you're transmitting the header, you go to the VM core. If you're going to the core, you go to the finished packet. But in the worst case, which is all packets get dropped 10 times, you pull 10 times for each transmit, and then retransmit 10 times. So you pull 100 times for each packet. That's 2 minutes and 30 seconds for one packet. If you're dumping a gigabyte, this takes like 2 days, something like that. And we have a terabyte. I didn't calculate that. Terabyte of RAM. So forever. So just don't even mess with it. You gotta fix this. Sorry?
Fix the network.
Well, so your network could have packet loss. Between two machines that I work with, I actually do have packet loss, so this would be horrible. But if you're dumping, say you have 10 machines that panic at once to one server, they're going to cause each other to lose packets. So even if your network works fine, you're going to be dropping UDP packets. You're just going to blow these queues. So that's the real problem. Is even if you configured everything correctly, you still lose packets, and then everything gets drawn way out. Because as you lose packets, it takes longer, and there's more machines dumping. It gets worse and worse and worse and worse. Hopefully, you don't have that many machines panicking at once, but you got to design for this kind of thing. Not sure I actually want to draw this, but one of the main problems is that you have to check your entire bit field every time. So this window is fixed, and you have to go back through every time, and every time there's a missing say you miss packet, I'm going to mess up. So here's your bit field. Let's say you have, sure. So you have four packets in your bit field. If you miss, let's do it. Okay, 0, 5. So if you miss packet 1 and 3, each time you go back through this loop, you're going to retransmit 1 and 3 over and over again. And then let's say you get, you retransmit 1, 3, and 5 every single time. And then you check, go back through this ACKS and say you keep missing 3. You're going to have to go through this every single time. You don't just retransmit, say, 1 until it works. So if you have a sliding window, you'd eventually just collapse until you're retransmitting the same thing over and over again until it works. So you can focus on what's not working instead of retrying everything every time. So you can slowly make progress. So the implementation is like a TCP over UDP. Implementation is not true TCP, but it's just UDP with flow control and sliding window. The aim is to reduce packet loss by throttling the sender to the rate at which the server can receive. This is the problem we were just talking about. So if you're receiving 10 separate dumps, you want to give them each 1/10 of your bandwidth so they don't start losing packets, and you can receive at the fastest rate possible. And then you expand your window as large as possible, but no further, so you don't lose packets. So you use AIMD to set the congestion window size. And that's dynamically advertised by the receiver based on how much bandwidth it has. You also use cumulative ACKS instead of having to ACK each packet separately, so you don't have to send 1 packet per packet received. That's a pain. And there's still no interrupts, so polling is required, but doing this, hopefully we can reduce packet loss hopefully to 0, but as small as possible so you don't have to poll and make as often. So currently, the performance is all right in ideal situations. Still not great, still not production ready for big systems. But with just the UDP stack as it was, dumping directly, then a switch in between a VM and your host, and dump at like 36.6 megabytes per second. But even this takes a while to dump a gigabyte or 10 gigabytes. And under packet loss, this rate is like halved very quickly. And then it can be brought to its knees if you have a lot of packet loss. It just becomes completely impractical. With the proper window, we should be able to at least double the speed. More importantly, I didn't write the rest of this in, but more importantly, it'll be a lot more reliable. Current status. I guess this isn't showing. Maybe I see what happened. Okay, so this should say current status. The IFLIB port is done, but TCP on UDP is not yet complete. I can slow down the transmit, so if you want a slower netdump, I can deliver that to you today. Yeah. But I can't yet dynamically expand and shrink the window. So we're not there yet. So work has become a full-time job. I used to have more time to work on NetDump, and then suddenly work became a 7-day-a-week thing. So the work on NetDump is ongoing because eventually we want it, but it's not yet ready for use. But if you do want to use it, sorry, I'm saving this. But if you do want to use it, if you want to try it out, Mark Johnson's NetDump tree works. That's ready to go. But what I would like to add is also at work, we work on SmartOS/Illumos, and it would benefit from NetDump functionality because it's often run diskless. And then implementing NetDump using an embedded TCP IP stack, like the lightweight IP stack, what LWIP stands for. might be the way to go instead of hacking on, or just nodding.
That was going to be my first question.
Okay.
You answered my first question.
Instead of hacking on TCP-like features onto UDP, it's much better to use somebody else's work. But that might be a large lift. I haven't actually looked into what this will take. But it will be a sizable amount of code pulled into the panic context and the dump routines. But that would provide you more flexibility than just TCP features on UDP. And something that gets debugged, not just by me or whoever's using it, but other people who use LWIP. And then implement support for Chelsea CC driver, because that's what we use on our machines. It'd be really nice if you dump at 100 gigs and dump your terabyte as fast as possible. So I want to thank Rogi Sato for hosting AsiaBSDCon, inviting me here to talk. Matt Macy for his work on IFLIB and his help with me working on IFLIB. And then Mark Johnson for his patches and help working on NetDump. If you want to look at this work, Mark's work is right here. Here's the NetDump server. That's in ports if you want to use it today. Then his FreeBSD development tree is right here. He has it. It's just a few commits on top of the tree, so you can pull those over as patches fairly easily. And then here's my work. FreeBSD dev is where you can get your slower NetDump if you'd like. And then my original work before I rebased on top of Mark's IFLIB port as opposed to mine is here. Is there any questions?
You guys can go first. One question.
Sure.
What about the encryption?
Oh, I believe it's supported. So you dump to a reserved memory segment using just the standard dump functionality. So that should all work as is.
Another question is what about what?
What about what?
Watchdog.
Watchdog.
Because now when you are creating crash dump, you can like say that okay, after this function bump the watchdog itself, but if everything is dumped, right? We create crash dump and we are sending it over the network, and especially with those transmission issue, the watchdog will just kill your machine, right?
I don't know. I haven't run into this. I'm not sure. Like, does anyone? I've never had watchdog kill the machine. So I've also never. How long is like the timeout?
You can configure it, but it's like seconds.
I've never seen it, and I've seen this timeout. So maybe so. Is it not on by default in the debug kernel?
It's from the OS hangs.
Yeah. It doesn't seem to. I'll check it out.
Another question. You said you have that slow version maybe readily available
Yeah.
for committing the code.
I don't want to commit the slow version.
Okay. So my point is, we have talked together about that yesterday, but I just wanted to be sure it lands in more people's minds.
Yeah.
There is at least one other application of opportunity to do network communication after the panic,
Yes.
which is network console. Linux has already this feature, and it's extremely handy for debugging the ports or machines that don't have any, that are headless and they don't have a serial connector, which is the case of with the Intel NVCs. And at least the netcons work that I have been doing would benefit from that extremely. And if we have something ready for usage or for adoption in the tree already, Google Summer of Code is upcoming, right?
Yes.
So that would be an interesting separate project. We could leverage someone else's time and work and motivation to do that. And as a result, we would have a generic, sure, it could be slow, but in the case of net console, we're talking about kilobytes anyway.
Right.
Not
Yeah, so for
gigabytes.
you don't need this performance work.
Right.
So you could just take advantage of Mark's work directly. And if you wired that up, it would be fine, right? Because you're just sending text. So that's not bad. getting your interactive part. So he's working. I don't know if everyone's familiar with netcons. I wasn't. It's a UDP like serial console.
Right.
And when his machine crashes, he has this set up. But when his machine crashes, he can no longer see it because he doesn't have his UDP stack. So he's interested in using this post-panic UDP stack. I think you could do it. You'd have to implement the receive if you did want to do the interactive
Receiver
part.
side is telnet or NC-U. I'm not doing bidirectional transfer yet.
Yeah, just one line.
For me, it's important to get just panic screen. Like where did it panic? Maybe with a stack trace, which is dumped automatically anyway. So I don't really need a receiving side, only the sending side, which also further simplifies the task. And yeah, the only thing is that the system cannot really do a UDP transfer after panic. And your work seems to cover just that.
Right. Yeah.
Okay, but I will add you as a possible point of contact for that possible Google Summer of Code project. Thank you.
Also talk to Mark.
Sure, thanks.
Sorry, I got the microphone. You're all tuned. So the LWIP idea isn't a bad idea, but you realize you can't allocate memory.
Right, so that's the issue.
That's the question. Have you, so almost all, many embedded operating system TCP IP stacks are cheap copies of the BSD TCP stack. Have you considered looking at some of those and doing what they did to our stack, to our stack?
That's
Instead of
probably
pulling
the way to
something as
go.
large as LWIP, you need to, I mean, you basically can't have timers, you can't have endless.
Right.
Right, but you could, you have a couple choices. You can spend the next year trying to reproduce all of the work that several thousand PhD students did over the last 30 years to GCP.
Right.
Or you can software engineer your way out of the problem. So LWIP is not a bad choice to look at. I can't remember what sort of reallocator it looks like.
Yeah.
But it's probably got a static allocator because it runs in very small things. So that would be the first thing I would do, because it's fun to build sliding window protocols, but it's not rewarding.
Right.
Um,
I don't want to, like, I'm fine with implementing it once, but once somebody's like, hey, this thing doesn't work, I know I'm going to be like, I don't want to do this anymore. I didn't sign up for this.
and yeah, no, I'm not going to suggest one. Pass that down.
Do you know of any specifically that you like?
LWIP is the one I probably would look at next.
Okay.
But whatever is used in RTEMS. So RTEMS is a BSD licensed open source operating system frequently used to make things that kill people. But other than that, it's very nice.
RTEMS, RTEMS.
And actually, Brooks Davis did an article on RTEMS in our previously. So that would be an obvious one with LWIP that would work out.
Do you know why Mark's work hasn't been committed yet?
So he was just, so in response to Ilya, he said, this is today, I don't know if you checked Fabricator, but he said it seems like he's ready actually. He was like, I don't want to add any more features, I want to just commit it. I think he's ready.
We can add more features later.
Yeah, that's sort of, I think, what he wants. But yeah, because it works.
It's only been like 18 years, right?
Yeah. What is it, 2004? Yeah. Some of the people born in 2004 are starting to program. Any more?